GPR, Qualitative to Quantitative Analysis. This whole topic area has been of great interest to me for many years, and it's been very interesting to see that we were starting to make major progress in the last decade. The purpose of the talk today is really to try and place some emphasis on the need for more quantitative analysis and set the scene. First, we'll go through and get a handle on what we mean by qualitative versus quantitative analysis. And then we'll provide some illustrations of what the evolution has been and where we currently are, and then look at some of the future opportunities. GPR is a fairly straightforward technique and is well known by many today. The vast majority of GPR measurements are relatively simple reflection profiling measurements. By this we mean that a GPR system, which is embodied inside this unit here, has a transmitter and receiver, and the system is moved over the ground along a relatively straight line to build up a transect or a cross-section of information. The same is on the right here, where we now have a towed system as opposed to a cart-based system. In both cases, the data is recorded and presented on a display in real time, and can also be recorded for post-acquisition. A critical part of the acquisition of data, of course, is also positioning, and modern systems will have GPR and GPS combined together. Why is GPR attractive and used widely? It's mainly because of the simple ray optics concepts that underpin the data that are observed. It's fairly straightforward for people to understand that if you have a transmitter emitting a signal, the signal will travel outwards and impinge on a target, and if it's reflected and scattered, will go up to a receiving sensor and can be recorded. In essence, the concept that energy travels along straight paths is very easy to conceptualize, and further, the signals are delayed as they travel along these paths, so there is a time delay associated with the signals. Time here depends on the path length and the velocity of propagation along the path. So as a result, we have some basic information and concepts which are readily grasped. The vast majority of GPR uses what's called the small common offset approach. Essentially, the separation between the transmitter and receiver is reduced as much as possible, so the transmitter and receiver are essentially coincident. When this happens, the distance to the target is the same as the path traveled, so that it's fairly simple to relate time to distance to the target. In the GPR context, this is usually referred to be depth. A GPR system traversing over the ground, as shown here, will have a certain view or illumination of the ground as the system travels along. It'll pick up targets, and it will trace out the distance to the target and plot it below the unit. The typical GPR reflection profile is shown here. The content is relatively straightforward in that we show the amplitude A of the signal versus spatial position on the horizontal axis here, and time on the vertical axis here. The actual signal amplitude is displayed as a grayscale shown here. Many different ways of displaying the data can be used, but the general character is that we recognize features by areas where there are strong amplitudes and the absence of features where there is no signal or weak amplitudes. Such as over here, this very weak amplitude. The key thing with this data set is that there's a very simple boundary showing up here. This is a soil interface, and it's very evident on the record. There's also a localized feature right here. This information can then be used for a variety of purposes. The essential information here is the amplitude and the at a given horizontal position and the travel time. We can use the additional sampled information to analyze, such as fitting a hyperbola to the localized target response. In this case, we can see the red line shows the response of a perfect point-like target superimposed on the picked response for the localized target in the previous slide. And we can do an estimate of velocity and depth based on the relationship between time and distance. This is then used to create the appropriate depth scale for the particular cross-section. Numerous of these steps might be entailed to get to the depth axis, which is shown on the left, and the time axis, which is shown on the right, so we have a relationship between time and depth. The key point here is that we use the amplitude as the piece of information that identifies a feature or draws our eye to it. Then we use the amplitude as that thing which allows us to join points, and the key information is the position and time, which follow a certain trajectory in the data set, and we can use that to make inferences about distances and depths and velocities. The amplitude information is seldom used for more than that purpose. What we have in this particular section is the use of amplitude for imaging. Again, it's really, we're making use of the position and travel time information, but in this case we display the amplitude either in a plan map form or volume form. In both cases we've acquired data over an area, over a number of lines or paths which cover a spatial area, and then transform the amplitude information into a color image versus position at a particular depth or time. On the left, what we see is the response of a drainage system under a golf green, and on the right we see the 3D rendering of two pipes which are buried in the subsurface. So what we have here is what we call qualitative analysis. The basis of understanding the data is quite intuitive. Targets really appear as contiguous sets of events in the space-time cross-section, and we use the amplitude to identify targets. The key outcomes are the presence and variation of layering in the cross-section and the location of local targets. All of these things provide a powerful tool for many useful applications, and we do not have to go much beyond the qualitative to get and derive much benefit from GPR data. The real question is, what are we missing? One of the things that always comes up is a desire for more information about the subsurface material. This is usually hidden in the material properties. Similarly, there's limited information about targets, so that we can't easily discriminate between different types of objects. We may have a localized target, but it could be a chunk of metal, a landmine, or a rock. and the ability to discriminate is just not there. We seldom extract some of the more complex spatial details of targets, and we have a very limited ability to sense gradual changes, since simple reflection data really is contingent on having strong gradients or abrupt boundaries or changes in material properties to give rise to the signal. All this is reality. On the other hand, the signal that we're actually dealing with is the electromagnetic field, which extends out through space and time around the measurement point. They're vector fields, and they are rich in information, such as these things which we're missing in the simple qualitative analysis. So, what do we mean by quantitative analysis? There's various levels of how this could be described, but essentially quantitative analysis gets down to using the amplitude for more than just an indicator of something being present. The amplitude information as a function of space and time contains a wealth of information if we can only unravel it. The amplitude of the signal by itself plus the shape of the signal in time contains a great deal of information about the material properties, the geometry, and all these things which we have yet to really been able to extract routinely. So, how do we go about this? What we really need to do is be able to predict what the value of A should be. And unfortunately, A is not easily predicted, since it depends on the whole signal path. It depends on the transmitter characteristics, the target characteristics, the earth that the target's buried in, and the receiver characteristics. So we have to know all of these things to be able to take, say, a voltage which we insert into the transmitter and be able to predict the amplitude at some space and time. Now, the key thing here is if we can set up a method of prediction, we can parameterize that prediction model, and then our job is to then find those parameters of the model which best replicate or represent the data we observe. This leads us to the whole realm of what we call geophysical inversion. This is true for all aspects of the model, in that if we change the electrical properties of the environment, we change the characteristics of the transmitter structure device. Similarly, for the receiver, we can all change some of the aspects of the amplitude data. If we can parameterize these things, then we have a way of understanding what the relationship is between the observed amplitude and all of the parameters which constitute the model. So the path forward to go quantitative is fairly straightforward, and there's nothing new here. Our ability to do it, however, has been limited and has only been getting stronger over the last few years. In summary, we know the fundamentals that are involved. We can do the mathematical analysis and set up the models, and we are now getting to the point where we can actually compute all of the component pieces of the model to actually generate the prediction. We can also understand how to do the predictions at various levels. It's not necessarily to quantify all aspects of the problem, but just some subsets of it, and assume the other ones are invariant or are controlled, so that we don't have to treat them in full detail. The key point is we cannot, quote, eat the elephant, quote, in one meal. This is a rather large, complex problem, and attacking it in stages, focusing on the low-hanging fruit and picking out those problems we can actually solve practically, is really what it's all about. So how do we limit the complexity of the problem when we want to go at it in a serious way? There are three primary ways we do this. One is to look for attributes in the amplitude that do not depend on the absolute values of the amplitude, but some characteristics of the amplitude that vary with the model structure. Another way is to address the problems where the amplitudes can be referenced. If we can measure at a fixed position and get a certain amount of information and then reference all other observations at that point, then we can eliminate a lot of common variables. This is commonly done when we use reflection amplitude information. The third way is that we simplify the system model and parameterize it by, say, a wavelet, and allow that wavelet to have free parameters which can be adjusted as we attempt to emulate the response from the Earth. So in other words, we have an Earth model and a system model, and we adjust the parameters of both till the amplitude we observe matches reasonably well. All of these can then be placed into an inversion process which will exploit the power of computers to extract parameters, quantify the uncertainty, and give us much better estimates of information in a quantitative form. One of the ways to see this is the water content problem. The water content problem is one which is common in agriculture and hydrogeology and has been there for many years. My first exposure to this problem was working with Clark Top and Les Davis when we did a lot of the pioneering work on the use of time domain reflectometry for water content. Since that time, it seemed that GPR should be able to provide the same kind of information, since the fundamental basics are the same. The goal is really to get water content in the soil and to map it out versus depth and lateral position, and in some cases monitor its variation with time over seasons, etc. When we attempt to do this with GPR, however, we hit a number of barriers and problems. For example, if we're using the direct ground wave, we wind up with having questions over what volume of the ground is really being sampled. So if that ground wave is traveling along the boundary between the air and the ground, how deep does it sense? And how does this depend on surface roughness and frequency, etc.? When we use the surface reflection method, we have similar problems, plus we get challenges with gradational variations. And finally, one of the things that does happen is that GPR doesn't uniformly average water content over a volume sensed. One of the serendipity aspects of TDR is that it's actually a linear weigher of water content, or very nearly so, simply because of the character of the measurement. With GPR, however, the GPR response is not sensitive uniformly over a volume, so that the average value is not necessarily the average volumetric water content, for example. So lots of challenges in this area, and the way they're addressed is to start going quantitative in analysis and being more sophisticated in how we approach things. One of the most interesting exercises was the surface reflection measurements, and we had done a number of these over the years, and in the late 1990s and early 2000s, Dave Redman and worked with groups at the University of Waterloo and the University of Guelph to assess whether or not we could actually make surface reflection measurements provide meaningful water content measurements. The assumption is pretty straightforward in that you put the GPR, which is shown here, and elevate it over the ground, and you measure the reflection from the ground surface, which bounces back to the receiver. In simple terms, the amplitude recorded there will vary with the changes in the ground dielectric properties, and one can extract the permittivity K here from the reflection coefficient. The reflection coefficient is determined by measuring the ground response amplitude and normalizing it against the amplitude over a metal sheet. When this is done, a lot of the system parameters are eliminated, and one has a fairly good amplitude tool for extracting the relative permittivity. The relative permittivity can then be used to infer water content using the top relationship or a similar type approach. So all in all, this looks fairly straightforward and simple, but when you do it in practice, you find that the data is very, very erratic. The plot on the lower right just is an example of some data from a survey that was done, and you can see the very highly erratic data in here, which did not seem to make sense. In fact, originally we attempted to attribute the variability to the rocking of the antenna system and orientation problems, or to surface roughness and so on. In the end, however, we were never able to demonstrate that we could get enough variability from this approach, and the averaging and so on, like we've shown here, still gave us a biased value. In other words, we did not meet the control data, which came from TDR and other measurements. So what was the cause of this? It turned out that it was the simple model for the reflection coefficient was not adequate. This thin layer has varying thickness in this particular analysis, so that we can look at what it does to the reflection coefficient. If we just simply varied the thickness, then we would find that if the thickness was 0, we would see the K of 10.1 and a water content of 20%. As the layer thickness gets bigger and bigger and bigger, we would find that the observed reflectivity would go down, ideally, and eventually we get down to the water content of around 5%. What happens, however, if you model the reflection coefficient, you find it follows the red dotted line, which doesn't give you a uniform linear decrease in the water content. As a result, what we're seeing here is that the GPR reflection is a much more complicated event, and it's not a direct tool for inferring the permittivity. We need to have a more sophisticated model with some sort of layered structure to it to accommodate the variability. If we look at the amplitude of the wavelet that this kind of a system would generate, we would also see that the wavelet shape was changing and the amplitude versus time was changing in such a way that we could estimate what the layering of the Earth was. So this area is one now of fairly active research, and there's a much more advanced analysis of gradational boundaries going on. Diamanti is giving a paper on gradational boundaries currently, and this study incorporates the full transmitter-receiver characteristics as well as the Earth properties and the boundary properties, and it's very clear that one can emulate all these things, and inversion is just a matter of time and computer power to implement. Simpler 1D models have been developed, and Sebastian Lambeau at Ghent and Evert Slob at Delft have worked on inversion processes for this type of approach with good success. Bottom line is that if you understand the problem and you can parameterize it properly and the model is close enough, you can do reasonably good amplitude analysis and quantitative analysis without a full system model, although this full system model is beneficial. Another topic area which is somewhat related is the use of the direct ground wave for estimating water content. In the simple model, one assumes the move-out slope when you vary the separation between the transmitter and receiver provides an indication of the ground permittivity because the slope is inversely proportional to the velocity in the ground. In reality, the ground usually will have some sort of gradient or layering from dry to wet or wet to dry, and that surface zone, which is relatively thin and can be small compared to the resolution length of the radar, actually becomes a thin waveguide which traps energy. This behavior manifests itself in the amplitude of the data by giving an en echelon type feathering to the direct ground wave arrival. Such is shown here. One can see that the group velocity or the move out of the ground wave is fairly straightforward, but the ground wave itself has a number of en echelon type events which are overlapping one another and moving out at a slightly different velocity. The use of a dispersion analysis provides an indication of the velocity versus frequency, and it pulls out the characteristics of the energy being trapped in the leaky waveguide, which is formed by the gradational characteristics. Using this information, one can then extract estimates of thicknesses and permittivity, such as depicted on the right, using an inverse process. This process can be quantified, uncertainty developed, and one of the key things to note is that the resolution of thicknesses is much higher than the typical resolution that would be achieved with the pulse duration and of a system like this, which is around 100 megahertz. So, all in all, it's very clear that the use of this type of approach works, and it's effective because you don't need to know the absolute amplitude, but the relative amplitude behaviors are used effectively. In the longer term, there's a great deal of work going on, and this focuses in on characterizing transmitters and receivers and looking at the detailed characteristics. We now have the tools to model these things very effectively, and we can start looking at some of the key characteristics of antennas, wavelets, and so on. The example shown here is that of modeling the full transmitter, receiver, and shield structure in a GPR system. The paper referenced by Diamanti gets into a lot of details about the shape of the wavelets emitted by the system and how they vary with angle and distance from the source. All of these things are crucial factors when one wants to attempt to simplify the full problem. While this particular analysis is very research oriented, one has to understand that in order to get the details right, one has to start discretizing the transmitter, receiver, and the ground system at very small voxel sizes. In this particular example, we have 1000 megahertz antenna system, and the voxel size is 1 millimeter on a side. So this very quickly becomes a very large, complex numerical problem to solve. However, these things are not insurmountable, and many changes are coming which make these types of analysis quicker and easier. And already some of these results are being built into inversion processes that allow full waveform inversion of data. Ultimately, we'll be starting to see full extraction of permittivity and conductivity and finer detail in targets than we've ever done before, and have some sort of quantitative measure of the quality of the result and the reliability of the result. So, systematic evolution of quantitative analysis is occurring, and it's going at a faster pace. One of the side factors that comes out of this is we need greater data fidelity and better understanding of system responses. Although we've come a long way, there's still a long way to go. One of the bigger problems has been computational power. For many years this limited what we could do, but it's becoming less and less of a barrier. In the future, we will see that the biggest challenges that will impede us will be the lack of funding and the limited number of highly qualified people who will be available to work on these problems and develop the sophisticated solutions that could be possible. So, thank you for attending this talk, and hopefully it stimulates some thoughts about what you would like to do and encourages you to contact people who are starting to do really successful quantitative analysis. The field is wide open for those with the interest and skill sets to attack it.